one of the most important reactions in the alcohol functional group is proton transfer. And so here we're going to focus on the Bronsted acidity and basicity of alcohols, just restricting ourselves to proton transfer for the time being. And really the place to start is to ask, what are the pKa's associated with this functional group? Alcohols are both weak acids and weak bases, and weak doesn't mean negligible. Weak means we need to think about it, but they're not the strongest acids in the world. The hydrogen of the hydroxyl group has a pKa of about 15 in water, and so its acidity is comparable to that of water, which in a structural sense makes great sense because an alcohol is essentially water with a carbon replacing one of the hydrogens. Protonated alcohols are strong acids, with the hydrogen of a protonated alcohol having a pKa of about -1 in water, which again is comparable to the hydronium ion, which has a pKa of 0. Although these aren't the world's strongest acids or bases, considering proton transfer in alcohols is still really important, and this is because protonation or deprotonation of that hydroxyl group, depending on whether we're in acidic conditions or basic conditions respectively, is a very common first step in reactions of alcohol. So this is often kind of the climbing up the hill type of step that kicks off a cascade of reactivity. Here's a reaction scheme for deprotonation of an alcohol, and the curved arrows here are the standard curved arrows for proton transfer. If we're thinking about water as the base, water donates a pair of electrons to the acidic hydrogen, and the OH bond breaks toward the more electronegative atom, oxygen. The Ka associated with this is about 10 to the -15th power, and that means the pKa is about 15. And this process generates the conjugate base of an alcohol, and this is called an alkoxide. This is a term we'll use on numerous occasions, and we'll often see alkoxide bases like sodium or lithium alkoxides used as bases in chemical reactions in the future. The conjugate acid of an alcohol is called an alkoxonium ion, and this comes from the protonation of the alcohol oxygen. Deprotonation of the alkoxonium ion is much more favorable due to the positive charge of the oxygen atom. And so if we again consider water acting as a base, removing this proton, we end up with a neutral alcohol now, an hydronium ion, and the Ka here is about 10, making the pKa -1. We'll often refer to this intermediate on the left here just as a protonated alcohol, understanding that the additional proton is living on the hydroxyl oxygen. Now we can kind of turn this idea of acidity on its head, right, and use these pKa's to think about the basicity of alkoxides and alcohols. The key conceptual idea is that the stronger an acid, the weaker its conjugate base, and vice versa. Quantitatively, we can say that RO-, the alkoxide, is a stronger base than anything whose conjugate acid, let's just call it HB, where B represents the hypothetical base B-, is less than 15. So RO- is going to be able to deprotonate any HB with a pKa less than 15. And this includes a number of very important functional groups in organic chemistry. So let's focus on the bases for which RO- is a stronger base, so the B-'s. For example, a carboxylate, the pKa of the conjugate acid, a carboxylic acid, is about 5, is one example. Phenolates, which are a type of alkoxide where instead of an alkyl group, we have a phenyl ring here. We looked at phenol, for example, in the previous video. Amines, RO- is a stronger base than an amine such as ammonia, NH3. And RO- tends to be a much stronger base than stable inorganic anions like Cl-, the conjugate bases of strong acids, Cl-, nitrate, sulfate. It's a much stronger base than these relatively stable inorganic anions. One other one that might be worth mentioning is cyanide. RO- has the ability to deprotonate HCN to form CN-. All that said, alkoxides in the grand scheme of things tend to find themselves close to the middle of the spectrum of basicity. And here, of course, we're looking for conjugate acids with pKa's that are greater than 15. And these are bases that deprotonate neutral alcohols favorably. These would be things like amide or amide bases, the conjugate bases of amines, NR2-. Pretty much any sort of carbon base, Cr3-, and even stabilized carbon bases, which we'll see later in the course, like enolates, CH2- connected to a carbonyl group. RO- is a weaker base than H-, and so hydride has the ability to deprotonate alcohols as well. If we turn our attention now to the neutral alcohol and think about the basicity of the lone pairs on the hydroxyl, oxygen, and neutral alcohols, the same theoretical argument applies, but our benchmark of pKa changes because now we're thinking about the conjugate acid of a neutral alcohol. Bases that are stronger than neutral alcohols includes anything whose conjugate acid pKa is less than -1. Now, so once again, let's think about the bases B- whose conjugate acid pKa's are less than -1. If you think about this, it's actually a very limited set, right? What acids have pKa less than -1? Well, that would be something like HCl, Cl-, nitric acid, HNO3, conjugate base is NO3-, sulfuric acid, H2SO4, whose conjugate base is HSO4- or SO42-. Really, ROH is only a stronger base than the conjugate bases of strong acids. And the important conceptual conclusion of all this is that only strong acids can protonate neutral alcohols. ROH is a weaker base than many other bases in organic and inorganic chemistry. And here now we just simply flip the inequality around. Any base whose pKa of the conjugate acid is greater than -1 will be a stronger base than a neutral alcohol. And of course, this is pretty much anything that's anionic based on N- or C-. And in fact, a few neutral functional groups are more basic than neutral alcohols. The most important is the amines. The lone pair on nitrogen is much more basic as a Bronsted base and as a Lewis base, really, than the lone pairs on the hydroxyl oxygen. So just to summarize now, we tend to find that alkoxides and alcohols are relatively weak as far as acidity and basicity goes in the pantheon of acids and bases in organic chemistry. What this means is that if we want to protonate a neutral alcohol, we need to use a strong acid to do it. The flip side is, if we want to deprotonate a neutral alcohol, we need to use a strong base. So often if we want to make RO-, for example, from ROH, we use something like hydride to do it. If we want to protonate an alcohol, strong acid is essential. HCl, HNO3, and H2SO4 are the three most common choices by far.